Let's now talk about the maximum margin classifier. So the maximum margin classifier can only be constructed for linear separable data. But something which is kind of intuitively clear is kind of, if we have linear separable data, I can find different types of separating hyperplanes, like I've seen in the previous picture, in the previous video, but there seems to be one which is kind of special, namely one which is just in the middle, such there's more distance to both of them. For example, if I to both classes, for example, if I had one type of classes here, I have another type of classes here, then obviously kind of this one here is very kind of close to the data point. This might have not been a good one, whereas this one here is also very close to the data points. Both are kind of separating the data, but there might be one, for example, like this one here, which is kind of furthest away to the data. And this distance here between kind of the closest data point on either side will give me this kind of zone, which is what is called the margin here. So I have, this is the margin here, and I have a wider margin. So I could ask like one very specific kind of separating hyperplane could be the one where I have the largest margin, and I could use this, for example, as a classifier, because now if I find this one, I can say, well, everything which falls to the left of it I will classify as cancer, and everything to the right as no cancer. So imagine for this data, I will kind of look and I will find the hyperplane which has the widest margin, which in a sense I could say is the most robust separating hyperplane, and the separating hyperplane will now be my classifier. Everything to the left of it will be cancer, everything to the right no cancer. So if I get a new point, say here, I will say this point will be cancer because it's to the left, whereas here this point will be no cancer because it's to the right. So I will kind of assign new colors to these new data points, and kind of here you can see this is just another way of plotting it as shown in the slides. So here I have the maximum margin classifier, where I look for the separating hyperplane which has the largest margins there, and you can see it nicely touches those 3 points. If I turned it kind of ever so slightly, I could make it wider until it nicely aligns with those 2 green dots, where it's kind of reaching the widest distance here. And you can also see that those 3 dots, they have a special role to play, because other dots seem to matter very little. Imagine I changed any of the points. Imagine this point here will now move over here. If this point moved over, or another point just shifted away, well, the classifier couldn't care less, basically. It doesn't change at all. Similarly, for any of the other points out here, if kind of one of this point would be moving, nothing really happens. But if any of those 3 points here moves, it will shift the whole hyperplane. If this point here would be moving thisward, then maybe my new hyperplane would be turning like this. If one of these points here, if this point would be moving inwards, for example, I mean, you can see how that happens. This is why those 3 points have a special name, and those are called the support vectors. This is where the name comes from. I mean, they're not called support points, but support vectors, because, well, there's always a vector which points towards them. As this is the origin, then obviously each point is represented by a vector x, and this is why they are called support vectors, because of the vector which kind of represents the point here. But those are the 3 vectors which support the margin, if you like. So if they change, then the margin changes. If any of the other points change, then nothing really changes in the whole picture in terms of the classifier. It won't move at all. So this is just about the kind of picture, what it means, or how can we write it down mathematically. And it's kind of interesting to see that, I mean, we already described the equation for a plane. If we go back a bit to what we discussed earlier, this thing here is the equation for a plane. But interestingly, if I look at this equation, so in general, a plane is given by this relationship, kind of beta 0 plus beta x equal to 0, which is the same as this result here, which is also equal to this result. So this is equal to beta times x minus a equal to 0. But interestingly, what would happen if x would not be on the plane here? What if x would be somehow outside of the plane? So I have kind of x here. Here's my plane. This is my vector a. And here's my vector beta. Beta is orthogonal to the plane as before. Now, this vector here will be x minus a. This is this vector here. Now, if it's orthogonal, then the dot product will be 0 between x minus a and beta. If it's not orthogonal, so or otherwise, what is actually this dot product here? What is this expression here? This is just the projection of the vector x minus a onto beta. So the length of this projection is just this length here, if you like, this distance here. Once I start projecting this vector onto beta, I'm taking the x minus a vector and I'm projecting it onto beta, then obviously if they're orthogonal, this projection becomes 0. But and kind of if they are parallel, then this projection is maximum basically. But what's also important is that if this projection here is positive, then the kind of x minus a vector is kind of pointing in the same direction as beta, which means like x is on the same side of the plane as beta is pointing towards. Whereas if x minus a times beta is negative, then x is on the opposite side of the plane where beta is pointing to. You see now beta is pointing upwards, and if x is above the plane, I would have beta x minus a being positive, but if beta x minus a is negative, then the point would be below the plane, so exactly opposite. And this is kind of what I'm just saying here in those equations. So effectively, if I have this relationship where this is positive, then I'm on the one side of the plane. If I have this relation with negative, then it's on the other side of the plane. But my classifier just says on the one side all the labels should be of one kind, and on the other side of the plane all the labels should be of another type. So now I would say, okay, if this is positive, so I'm kind of above the plane, I will choose the labels to be 1, and then I'm kind of below the plane, I will choose the labels to be -1. And here's where the nice notation comes in, because effectively, because I have this plus minus 1 chosen rather than 0 and 1, I can write this in one single equation here. So for all points to be correctly classified, what I need is to have yi times f of xi being bigger than 1 for all I. This encapsulates both the relationship, because here in this case, if y is equal to 1, then this result will just give me f of xi bigger than 0 for yi is equal to 1. But if it's smaller than 1, if it's -1, I will get minus f of xi is bigger than 0 for yi equal to -y. But this is just equivalent to f of xi being less than 0, which is the second relationship here. So effectively, this one equation gives me those two relationships, relationship 1 or relationship 2, for either of these cases, 1 or 2 here. So I can compactly write it in this form, which is a very nice thing to do. And interestingly, and this again goes back to before. Now, if kind of, I already discussed here that if my point is not on the plane, and now it got a little bit messy here, but if my point is not on the plane, then this difference here is just a projection. But if beta is normalized, then it will just give me the length of this red line here. I will get exactly the length of this vector if my vector beta is normalized, because I know that beta times x minus a is nothing else than the length of beta times the length of x minus a times the cosine of the angle here between the two, this angle here. But then if the length of beta is equal to 1, then this term is equal to 1. And this second term is nothing else but the length of this projection here. So this is something important as well to notice, and apologies if it got a little bit cluttered here. I should have maybe introduced a new page rather than trying to add it to the existing one. But all we see is that kind of this relationship just says this thing here or this thing here is nothing else but the projected length of this difference. How far away is the point? So if I have the plane here, I have a point here, this is the normal vector, then effectively this thing here is nothing else but this distance here, the distance of the point away from the plane. And effectively I'm saying if this distance is bigger than m, then I'm outside of the margin. If I assume I have a margin here, and I effectively say here's some distance m, and there's also distance m to the other side. So I'm kind of choosing my margin 2m wide. So m is the margin on either side of the plane here. So this relationship here just tells me that if this kind of distance, which is exactly the projection of this vector x minus a I saw earlier onto beta, and for this I need beta to be a normal vector of length 1, if this distance is bigger than m, then I'm outside. So then any point I choose happens to be just outside of the margin. So if it's equal, then it's just on the margin. If it's bigger, it's somewhere outside of the margin here. Now this is just, well, the picture I've shown is just true for yi equal to 1, but it works equally on the other direction. Then effectively I'm looking at those points here, which are all the ones where the projection is negative, and then, but then the equation will still be the same, exactly as the equation on the previous case encapsulated those both cases where I'm above or below the plane, if this is bigger or equal to 0. Now if I choose this beta to be a normal vector, then yi f of xi bigger or equal to m will just tell me now I'm not out above or below, I'm above or below some margin of width m above or a margin of width m below. So total margin here of 2m for the total width of the margin. So I'm outside of this margin. So this is exactly the condition which I need, and effectively, and now it's getting a bit cluttered here, but effectively my optimization problem for finding the maximum margin classifier would just be maximize the margin. Well, really I want to maximize two margins, but that's the same as maximizing the margin. So I want to maximize this margin around the plane over all my coefficients, beta 0, beta 1 and so on, such that all points lie outside of the margin. In particular, all points of label +1 lie outside of the margin on the one side, and all labels with -1 lie outside of the margin on the other side. And this is exactly given by this equation, assuming that beta is equal to 1 in length. So I'm kind of optimizing over all betas, but with the constraint that beta is equal to 1, and with this constraint, oh, now I deleted it. This constraint just tells me what I was trying to show here, but it ended up a bit messy, so I'm deleting it, maybe redrawing it. So I have my hyperplane, I have this margin here. This distance here is m. This distance here is also m. And I'm saying any point of class +1 must be outside of this margin on this side, and any point with class -1 must be on the margin outside on the other side here. And them being outside of the margin is exactly given by this expression here, which hopefully was clear. This thing being bigger equal to m would just tell me it's outside of the margin, but only if I had chosen beta to be of length 1. So my optimization problem becomes maximize the margin such that all points are outside of the margin, which is given by this first equation if beta has length 1. And this is kind of the equation for the optimization problem for the maximum margin classifier. So if you wanted to find it with your computer, you will just look for that, try to find the largest, or try to find the coefficients beta 0 to beta 1, which will define the plane such that the margin is widest. It's a bit like what we were doing here by eyes. If we started to rotate the lines, once we see the one which looks widest, that is exactly which optimizes this objective function. And here I have an example of how this would look like. These are some real data points, the circles and the kind of black circles and red circles. And here I can see the kind of the maximum margin classifier, which would be this middle red line here. This is the margin here of width 2m, and those three are the support vectors. And as I said, everything which is on the one side I will classify as one label, and everything to the other side as another label. Even if I found the classifier using the maximum margin, and I'm kind of requiring that none of my original data points lies within the margin. Now, if I were to find a new data point which happens to be inside of the margin, like this one here, I would classify this one as of the class +1, whereas if I find a new data point here, I will classify it as a class -1, so even if it falls within the margin. So this is how the maximum margin classifier works. We saw it both in terms of pictures as well as in terms of math and what the optimization problem is, which is often always important if you want to kind of implement it on a computer. But as we mentioned earlier, for most data we do not have this property that is linear separable, so we will never be able to find a maximum margin classifier, and that's why in the following we want to kind of relax a little bit this condition that the data must be linearly separable, and that naturally takes us to the support vector classifier, which also is a linear classifier but which does not require linear separable data.